So our radial stress, or sorry. So if we have, so in this video we're going to talk about how we can calculate the radial stress within an element. So, uh, so if we have a small differential radial element, um, it'll have the inner radius of the element here. It'll have an outer radius, or a radius at a given point, which we'll call that point R1. All right. The area going from the inner radius to that point will be called that area A1, and then it will have our tangential stress sigma theta on both sides of the element, and then we'll have our radial stress sigma r. So in order to calculate our sigma r, what we're going to do is we're going to sum all of our forces in the y direction. All right, I set it equal to 0. So the first thing we're going to do is we're going to determine what is the portion of sigma theta that is due to our radial stress. So if we look at our radial stress, we can kind of treat it like a triangle where the y-axis would be equal to the small angle theta over 2. So the y component of our radial stress we can think of as being equal to the y component would be equal to sine of sigma theta over 2 times sigma theta. Right. So if we plug that in and we integrate it across the whole cross-sectional area, we would get our radial force due to our tangential stress being equal to negative sine delta theta over 2. We can simplify this down because delta theta over 2 is very, very small, so we can approximate it as sine of delta theta over 2 as just being equal to delta theta over 2. And then if we look at the stress in the bottom of our element, we can multiply our radial stress by the cross-sectional area. So the cross-sectional area would be equal to our arc length, which would just be equal to r theta. And we can then, let me see, and then we would have the width of this section would just be equal to b. Okay, so so if we add all three sides of our equation together, what we end up getting is we can set our radial stress equal to 1 over br1 and integrate d theta dA. So if we plug in our value for d theta, or sigma theta, if we plug in our value of sigma theta dA times dA, we end up getting this equation here for our radial stress. So the sigma theta is just from earlier in the lecture. Okay, so um, let's see here. So R1 is just at the point of interest that we're interested in solving for. So that's the stress at the point that we're solving for. And A1 is just the area of the area up to the point of interest. So it's from the inner radius to the point of interest, R1. All right. So we're going to use this definition here to do a simple example problem of how you can calculate the radial stress for our simple clamp problem that we've been working on over the last few videos.